because Assignment Discovery is shining light onto some underappreciated elements known as the Lanthanide series.
First, we'll look at the unique chemistry of these elements in Exploring the Lanthanide series.
Then, we'll watch stories come to life in Lanthanum Movie Magic.
Next, learn about the value of currency and how it is protected in Neodymium Magnetic Money.
Then, we'll look beyond the television screen in Europium Seeing Red.
And finally, we'll get a high-tech tour of an Air Force secret weapon in Super Laser.
Elements that play a vital role in our everyday lives. Coming up next.
As you watch the first half of this program, keep these questions in mind.
What are some properties of the lanthanide elements?
What is the relationship between lanthanides and color television?
Most lanthanide mineral ores contain a mixture of most of the elements from the Lanthanide series. This caused scientists trouble for years because they were unable to tell the difference between several of the metals.
Have you ever mistaken two similar things?
I've mistaken words many times, actually.
When I was little, I always confused synonyms and homonyms. I'm not really exactly sure what the difference is between them now either.
I've mistaken different people for people I know.
I used to think that leopards and jaguars and cheetahs were all the same.
My girlfriend and my girlfriend's sister, whenever I call them and her sister picks up the phone, I usually like, hey baby, or something like that. And it's your little sister, and I usually screw that up a lot.
The group of elements known as the Lanthanide series lies at the very bottom of the periodic table. The lanthanides share some properties with the transition metals, including high melting and boiling points. They also react easily with oxygen and water and dissolve in acids. Although they are a subseries of the transition metals, the series is usually considered a separate group. The group typically includes the 15 elements from lanthanum to lutetium. Most lanthanides have a shiny silvery or pale gold appearance and are all solid at room temperature. The lanthanides are commonly used for specialized lighting, lasers, and magnetic applications. They are also called the rare earth metals because when they were discovered, they were very difficult to isolate, so scientists thought they were uncommon. In fact, the elements in the lanthanide series are quite common. The only lanthanide not found on Earth is promethium. All of its isotopes are radioactive, so any promethium that may have existed on Earth at one time has decayed into other elements. The lanthanides are difficult to isolate because they closely resemble each other at the chemical level. This similarity is due to their electron configurations, which can be explained by a close look at the periodic table. The elements are listed in order of their atomic number, which represents the number of protons in an element's nucleus. In its normal or ground state, this nucleus is also surrounded by an equal number of electrons. As you read the periodic table from top to bottom, each horizontal line is called a period. Each period represents the number of electron shells the element's atoms normally have. The lanthanide series is entirely in period 6, since every atom has 6 electron shells. The electrons in this outermost shell are called valence electrons. It takes 8 valence electrons to fill an outermost electron shell and make an atom stable. For most groups on the periodic table, the number of valence electrons an element has corresponds to its position on the table. For instance, sodium in group 1 has 1 valence electron, and calcium in group 2 has 2 valence electrons. But the lanthanide series is different. Each lanthanide has 2 valence electrons in the s orbital of its 6th level shell. But some also have a free electron in an interior d orbital of their 5th level shell. And as the atomic number of the lanthanides increases, additional electrons are added to another interior orbital, the f orbital in the 4th level shell. Each orbital in an atom is made up of suborbitals, which can hold 2 electrons each. The number of suborbitals determines the number of total electrons in an orbital. The s orbital is made up of a single suborbital, so the maximum number of electrons it can hold is 2. At the other extreme, the f orbital consists of 7 sets of suborbitals, so it can contain a total of 14 electrons. Just as atoms are most stable with 8 electrons, suborbitals are most stable with 2 electrons. To make the most stable atom, electrons in certain lanthanides jump between the f and d orbitals. The lanthanides are so similar because as an atomic number increases, electrons are added to the innermost f orbital instead of the valence shell. This minimizes any effect the additional electrons have on the properties of the element. Because they are similar, lanthanides need not be isolated to be useful. One of the most common uses for the lanthanides is mish metal, a metal mixture used in steel production, magnetic alloys, and vacuum tubes. It is approximately 50% cerium, 25% lanthanum, and 25% other lanthanides. Did you know? The lanthanides played an important role in the discovery of nuclear fission. The German scientist Otto Hahn noticed several lanthanide elements in samples of uranium. His colleague, Lise Meinter, realized this meant that uranium was undergoing fission, and the products of the reaction were lanthanide atoms.
Everyone knows about mood lighting. Movies take that concept to the extreme by creating whole environments out of specialized lighting design.
How important is lighting in the movies?
I think it's really important. I think it sets the tone of the scene and also the mood of the characters, and it could probably, I'm not an actor or anything, but it probably helps like them get in the mood.
Lighting is really important in movies because, you know, you don't want to watch a romantic scene in the school with this lighting because it's not going to be very romantic with the fluorescent lighting, bring out every flaw that the actors have ever had on their faces.
That's what attracts the audience, I feel like, and it also affects the mood of the movie as well.
Element number 57 on the periodic table is lanthanum. The atomic symbol for lanthanum is La. A shiny silvery white metal soft enough to be cut with a knife. Lanthanum is one of the most reactive of the rare earth metals, and it forms a bluish oxide. The name lanthanum comes from the Greek lanthano, meaning to lie hidden. Lanthanum is classified as an element in the lanthanide series. It lies in the periodic table 6th row, period 6. Each atom of lanthanum consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of lanthanum, its nucleus has 57 positively charged protons, plus 82 uncharged neutrons. Lanthanum has 57 negatively charged electrons to balance its 57 protons. These electrons are found in 6 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, xenon. Xenon has 54 electrons distributed among 5 orbital shells. Lanthanum has 3 more electrons than xenon. The first 2 electrons are found in the sphere-shaped 6s orbital shell. The final electron is found in one of 7 lobe-shaped 4f orbitals. Since the electron in the 4f orbital is at a lower energy than those in the 6s orbital, only the 2 valence electrons in this 6-level shell influence how lanthanum interacts with other elements. Lanthanum oxidizes rapidly when exposed to air, forming lanthanum 3 oxide, which is dark gray in color, as seen here. In reactive metals such as lanthanum, the oxide spalls, constantly exposing fresh metal. Spalling is the spontaneous separation of a surface, and it allows corrosion to continue unabated. Lanthanum is used to make lights used in the motion picture industry for studio lighting and projector lighting. It increases the brightness and provides light very similar to sunlight. Because it gives glass refractive properties and is resistant to alkalis, lanthanum oxide is used in manufacturing camera lenses. Lanthanum is also used to make flints for lighters. The dream of traveling to the moon has long sparked the human imagination. To chronicle space travel in the motion picture From the Earth to the Moon, the producers wanted to capture the drama and meet the viewers' expectations of the actual events of the first Apollo moon landing. The producers wanted viewers to do more than see a movie about landing on the moon. They wanted them to experience the terrain of this celestial body. No details were spared. The film crew worked closely with NASA, even borrowing a real lunar module for the set. They trucked in tons of dirt and rocks to simulate the surface of the moon and duplicate the lunar landing site. Actors wearing genuine Apollo spacesuits were attached to huge helium balloons to create the experience of lower gravity. All of this would be nothing, however, without the art of lighting. This movie set required a light source powerful enough to illuminate a space the size of an airplane hangar, yet sharp enough to appear inches away from the astronauts, emulating the confined environment inside the space capsule. Lighting designers achieved such precision by using carbon arc lamps. These high-intensity lamps contain the element lanthanum. Their intense white light is due to compounds of this rare earth metal. A carbon arc lamp uses an electric spark to generate heat between 2 carbon electrodes. The heat causes the electrodes to vaporize and burn. Lanthanum is inside the carbon rods and acts as a conductor. The reactivity of the lanthanum causes the lamp to burn brighter than with just the carbon by itself. Lighting was especially important in recreating scenes on the moon. Objects cast darker shadows because the moon has no atmosphere. The chemical properties of lanthanum and other rare earth elements have helped us get a glimpse into another world. Did you know? Carbon arc lamps were widely used before Edison invented the incandescent light bulb. Incandescent light has replaced carbon arc lamps in everyday situations, but movie makers still rely on these bright lights on the set.
Ever since the force of magnetism was discovered by ancient people, it has become a vital part of human lives, and it has many surprising applications.
Where can you find magnets?
I have a lot of magnets in my refrigerator, actually.
I know that magnets are used in compasses to find north and south.
TVs and computers, I know, too.
If you're sick or you have some broken bones, you can take an MRI, that's magnets.
Electromagnets are in a lot of things, like they're in generators that turn turbines.
I have a lot of magnets on my refrigerator.
My sister has magnetic earrings. It's kind of cool.
Element number 60 on the periodic table is neodymium. The atomic symbol for neodymium is Nd. A bright silvery metal, neodymium readily oxidizes in air. Neodymium takes its name from the Greek words neos and didymos, which mean new twin. Neodymium is classified as an element in the Lanthanide series. It lies in the periodic table's 6th row, period 6. Each atom of neodymium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of neodymium, its nucleus has 60 positively charged protons, plus 82 uncharged neutrons. Neodymium has 60 negatively charged electrons to balance its 60 protons. These electrons are found in 6 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, xenon. Xenon has 54 electrons distributed among 5 orbital shells. Neodymium has 6 more electrons than xenon. The first 2 electrons are found in the spherical 6s orbital shell. The remaining 4 electrons are distributed among 4 of the 7 lobe-shaped 4f orbitals. The 2 valence electrons in the 6s orbital shell influence how neodymium interacts with other elements. Neodymium is best known for its strong magnetic properties. In this experiment, a ferromagnetic fluid reveals the lines of force around very strong neodymium magnets, causing a hedgehog effect in the fluid. Neodymium is a component of didymium glass, which is used to make goggles for welders and glassblowers. It can also be added to glass, enamels, and glazes to add color. Some types of neodymium glass are used to create artificial rubies for lasers. And neodymium is a key component of permanent magnets in electronics and currency detectors. The United States dollar is one of the most recognizable currencies in the world.
Our currency is very traditional, one color on each side, the same size all the time, the same people depicted. It is something that we value. It's the American public values. There's a sense of trust, faith, confidence that we have in that currency, and we don't take lightly to the idea of change.
And it is one of the world's most valuable. This makes it a ripe target for counterfeiters. Currencies around the world use different methods to protect their value and identify fakes. The red plastic window in this Brazilian note can't be reproduced by a copier or scanner. Neither can the watermark on the British pound. Intricate color schemes, complex designs, and a variety of sizes are other security features. The United States relies on several measures to safeguard its paper money. One of the most basic is magnetism. The secret is in the ink, and it's a well-kept secret. But the basic principle is that ingredients in the ink used to print US currency has some magnetic properties. The magnetic signature is a first line of defense in the battle against counterfeiters. And permanent magnets made of neodymium are an invaluable weapon. Neodymium iron boron magnets, known as NIB magnets, are the strongest magnets made. They are so sensitive that a very small one can detect the magnetic field of a dollar bill, including its denomination. Bills suspected of being counterfeit are sent to the U.S. Secret Service, where tests are run.
Here in Counterfeit Division, we see everything ranging from this highly deceptive $100 note that's produced in Colombia, all the way down to this inkjet-produced counterfeit $100 note that was probably produced in someone's basement or garage.
At the Secret Service, workers compare every new fake bill to samples on file, searching for patterns and clues that may lead to the counterfeiters. It may take months or even years before a counterfeit ring is broken, but detection is key, and thanks to neodymium magnets, fake money stays out of the mainstream. Did you know? The U.S. Secret Service was created a few months after Abraham Lincoln's assassination in 1865. But its original mission was to protect U.S. currency from counterfeiters, not protect the president. That task didn't take place until 1902, when Teddy Roosevelt was in office.
Television is one of the most influential inventions of the past 100 years. It keeps us informed and entertained, but it also can take time away from other activities.
What do you like or dislike about television?
I like that for TV you get plenty of entertainment.
Well, there are certainly some shows on TV that can provide you with information to know more about what's going on around you.
I like to watch TV to relax.
I like the realism of TV.
I definitely like reality TV. I'm a big fan of that.
What I don't like is that it can have a negative influence on its audience.
Commercials all the time.
Well, I dislike that there are a lot of the same things on.
You start kind of becoming addicted to it.
When, like, you look up at the clock after a while, and you see that it's been like 2 hours and you could have been doing other things that are probably better for you.
Element number 63 on the periodic table is europium. The atomic symbol for europium is Eu. Europium is a soft, silvery metal. A sample of crystals with a green oxide coating is shown here. Europium is named after the continent Europe. Europium is classified as an element in the Lanthanides series. It lies in the periodic table's 6th row, period 6. Each atom of europium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of europium, its nucleus has 63 positively charged protons, plus 90 uncharged neutrons. Europium has 63 negatively charged electrons to balance its 63 protons. These electrons are found in 6 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, xenon. Xenon has 54 electrons distributed among 5 orbital shells. Europium has 9 more electrons than xenon. The first 2 electrons are found in the sphere-shaped 6s orbital shell. The remaining 7 electrons are distributed among the 7 lobe-shaped 4f orbitals. Only the 2 valence electrons in the 6s orbital shell influence how europium interacts with other elements. Europium oxidizes rapidly as soon as it is exposed to air. Here, the metal is shown over a period of 8 hours. First, it reacts with oxygen, and then the oxide combines further with carbon dioxide to produce a yellow carbonate. Europium metal has no commercial applications, but europium oxide is widely used with yttrium as a red phosphor in television sets. Today, it is impossible to picture life without television. This box of light and sound keeps us informed and entertained. But TV is a relatively new invention, and color television is barely 50 years old. TV was first introduced to the public at the 1939 World's Fair in New York. Development went on hiatus during World War II, but when the war ended, the television industry exploded. The first televisions were small and showed pictures in black and white. Television cameras originally used vacuum tubes to create video signals from images. Light striking the front of a glass tube coated with a photosensitive compound would leave an electric charge in the coating. A beam of electrons scanned the tube from behind and turned the image into a stream of electric current. Inside a television set, a similar beam of electrons transmitted the image information onto the glass screen. The electron beam scanned back and forth across the screen, and it activated phosphor on the screen, which lit up. The glowing phosphor created the image viewers could see. But the world was full of brilliant color, and only color TV could capture what reality looked like. In 1954, RCA was one of the first companies to produce color TV. The basic operation is the same as black and white television, but a few adjustments allow the transmission of color images. A color TV is coated in phosphor, but it uses 3 phosphors instead of 1, and each gives off red, green, or blue light. Europium is the primary component of the red phosphor. In a color camera, a prism splits the image into red, green, and blue light. Splitting the light allows the electronic signal to encode color as well as brightness. When the electronic signal reaches the TV set, the electron beam strikes either the red, green, or blue phosphor, depending on the signal. The blending of colors on the screen gives an accurate color image. Television has taken a permanent hold in human society. With the help of Europium, we get an accurate image of the colorful events that change our lives. You've been given all the information. Now it's your turn to discuss the questions. Take a moment to talk about the following.
What are some properties of the lanthanide elements?
What is the relationship between lanthanides and color television?
If you'd like to learn more about what you've just seen, go online or check out these books at your local library.
As you watch the second half of this program, keep these questions in mind.
How do lasers work?
How does the military rely on science?
When lasers were first invented, they were little more than a scientific oddity with few practical uses. Now much of the technology we use every day requires lasers.
How are lasers used today?
Lasers are used for a lot of different reasons, I guess.
Laser tag?
I know they use them in guns.
Do some laser eye surgery.
Laser pointers, to use to annoy people.
Usually in printers and probably eye surgeries.
I guess secret agents use them.
Within the U.S. Air Force is a community of scientists whose secret experiments have released a powerful new force: laser light. At its pinpoint of focus, laser light can be more intense than the sun. The purity and dazzle of a laser beam is an image straight from sci-fi fantasy.
Sequence start. Ten, 9, 8, 7,
Lasers can unleash terrifying force.
4,
This Air Force laser is the most powerful of its type in the world. It produces a narrow beam of 150,000 watts, enough energy to light up a football stadium focused onto a spot the size of a pinhead. The toughest materials are destroyed. Polycarbonate, which is so strong it's used in aircraft windshields, is baked into soufflé. Titanium, which melts at 1,600 degrees Celsius, is vaporized. A laser beam appears to be the perfect weapon. It strikes the target at the speed of light and with lethal accuracy. But the laser's pioneers did not set out to build a death ray. Working in Hughes Labs in California in May 1960, Ted Mayman wrapped a rod of ruby inside a flashbulb and brought a new kind of light into the world. He had invented the laser. The official press release boasted, "Man has created atomic radio light, brighter than the center of the sun." Even Mayman was amazed by the shocking red of its beam. It was beautiful, but weak. It couldn't melt chocolate. And for some years, most laser pioneers remained skeptical about turning the new device into a weapon. As Nobel Prize-winning laser scientist Arthur Shallow revealed to Walter Cronkite.
We hear so much stuff about high-powered lasers and what sort of dangerous weapons they are that we had a little fun. We built up a little demonstration laser.
That's a dangerous-looking weapon there. It looks like a rocket gun.
We couldn't shoot the students. They were all paying high fees, and professors were somehow out of season. So we thought, well, got to get some animals. So we went to the zoo, but they didn't want us shooting their animals. So we just bought a balloon for the children. And but you know, when we got that balloon, there was a mouse in it.
You know how mice get into everything. However, we had our more or less trusty laser.
So we took our more or less trusty laser,
and we were able to dispose of it.
Now, isn't it possible to build a lethal ray gun?
Maybe someday it'll come, but it isn't here yet.
In the 1960s, it wasn't the power of laser light that caught the imagination. It was the look of it.
It doesn't look like ordinary light, and as you move your eye slightly, it appears to sparkle. The very pure colors, particularly when you get the multicolored lasers, are gorgeous. Yes. Yeah, I'd love to see that.
Arthur Shallow wasn't the only scientist dazzled by the laser. It immediately appeared in many lab experiments. But some early lasers were useless. Critics accused it of being a solution in search of a problem. Lasers did have some early successes. Among them were eye surgery, welding, cutting, and holography. But the science fact of laser weapons still lagged far behind the science fiction.
Flash, what are those awful creatures?
I never saw anything like them. They must be from another planet. This ray gun ought to stop them.
They're not human!
Any comic strip artist knew that lasers should be able to blast tunnels through mountains or shoot down Klingons a million miles away. Well, I calculated that with the kind of lasers we had then, if you could deliver a flash of 1 joule every second, which was much more than we could do, you could completely evaporate a 200-pound man if he'd stand there for 3 years.
The New Mexico desert has been the site of the ultimate weapon. This is where the first atom bomb was built and tested. The researchers here hope to follow that legacy. Laser weapon development began here in the late 60s. 30 years later, Kirtland Air Force Base has become the home of the super laser. Its motto is, peace through light. There are now 5 high-energy lasers on this base, and more than 100 scientists work on them. Kirtland's first breakthrough was in 1973. The officer in charge was Major General Don Lamberson.
This was the site of the first high-energy laser experiments against moving targets. There was an enthusiasm and a momentum for doing something new that had not ever been done before. And I suppose if we had understood the challenges that lay before us, we would have given up at that particular point in time. But we didn't, because it was an enthusiastic, young group. Let's go get the job done.
This film reveals the trial of the first laser weapon in 1973. It weighed more than 30 tons and needed a crew of 4 to aim and fire it. The weapon's massive fuel tanks and optics covered an entire half-acre hill. The largest optic was a tracking telescope, which was used to aim the beam at an unmanned drone plane.
Now, there were some sergeants from Fort Bliss that operated the drone, and they would launch the drone, and the drone would typically fly a racetrack pattern around there. On the first event, the drone cut the corner a little too short, and as a result, the beam caught the top of this weather tower right here, and since the tracking of the beam was done by infrared energy, the beam said, I like that, that's a hotter spot than the drone, and I'll just stay right there, and it melted the top of the tower, which has since been replaced.
The sergeants launched a second drone and directed it to fly along the valley, almost a mile away from the laser. At this distance, the 12-foot drone was just a tiny, fast-moving dot in the sky. It was a tense moment for Don Lamberson and his crew. Another miss, and their vision of laser weapons would be finished. Eventually, the beam locked onto the drone's engine, and then took just over a second to burn a small hole in the steel fuselage, just below the wing. The fuel tank exploded, and the drone broke in half. The decapitated engine parachuted down, landing almost 300 yards away from the body of the drone.
At last, there was a system which could reach out at the speed of light and can destroy a target very much as a missile or a gun would destroy the target, except that it's going at the speed of light. And so, while that had been the work of fiction before, and while we were sure that that would happen, it had not been demonstrated until November of 1973.
The crew gathered around the debris. They thought that a fighter armed with a lethal laser striking at the speed of light would be invincible in the skies.
We never were able to bring the size and the cost of the laser down where it was compatible with fighter aircraft.
Kirtland had come up against a fundamental dilemma in building a practical ray gun. The smaller the laser, the less power it has. This stems from the way a laser creates its beam of light. Arthur Shallow has a vivid explanation.
It's a bit strenuous. I have to take off my coat. You see, from the beginning of time until the last few years, all light sources were hot bodies, like the sun or the gas in a neon sign. As the atoms are heated, they're forced to knock against each other, and some of them get excited. And then they emit in a millionth of a second or so a little flash of light. And you have one here, ping, a lot of ping, 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 ping. And you have big ones go ping, 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 ping. So you have just a jumble.
In other words, the light goes everywhere. To turn this general glow into a beam of laser light involves playing a trick on the laws of atomic physics. This laser is a glass tube filled with gas. The atoms that make up the gas are being bombarded with electricity to make them excited so that they emit light waves. At each end of the laser is a mirror that some light waves traveling in harmony bounce off. These light waves head back into the gas, forcing other already excited atoms to release more light. As more atoms are forced to release light, powerful light waves build up inside the gas. Eventually, they burst through one of the mirrors. The amplified light waves are in perfect harmony. This is a laser beam. Not all lasers use gas. Solid-state lasers use ions that are suspended in a crystal matrix. Many of these lasers rely on lanthanide ions in a matrix of another lanthanide crystal. One of the most common involves neodymium ions in an yttrium aluminum crystal. In solid-state lasers, the ions are excited by an external energy source, and the beam is produced in a very similar way to a gas laser. While the crystal matrix theoretically has no effect on the strength of the beam, different crystals can cause variations in the laser. By injecting more energy to create more excited atoms, the beam's power is increased. But as the energy input grows, the device that contains it must grow too. Most early high-energy lasers grew so big, they never left the labs they were built in.
We clearly had in mind that we needed to show the physics and the feasibility of a high-energy laser from an aircraft platform. It didn't need to be a fighter, it didn't need to be a bomber. That was terribly important to get from a stationary ground situation to a moving situation in the air.
Getting a laser airborne would take a big plane and a brave crew. In October 1980, the Airborne Laser Lab lumbered down the runway for its maiden flight. The laser inside was so heavy, the plane could only carry enough fuel for a 4-hour flight. But after a few years, the Airborne Laser Lab began a series of experiments to see if it could intercept and destroy a Sidewinder air-to-air missile, which was traveling at more than 2,000 miles an hour. There was only one way to test this capability, and it was very hazardous.
This aircraft was serving as a target and was being shot at by a real missile from a real aircraft. If it had been hit, the aircraft would have been destroyed.
So as a precaution, the missile did not carry enough fuel to reach the Airborne Laser Lab.
-5, clear to Fox. But there was a finite probability that it would happen. And that was if the airplane that was launching the air-to-air missile toward us, if he pitched up, if he actually flew up like that and launched it during that process, then there was enough energy for the missile to arch over and come toward us. That happened one day. Our chase airplane, the man who was flying with us watching what was happening, disappeared. He was history. This airplane's not getting out of the way of anything. And we sat quietly and watched this missile come in toward us, and in the screen, you could see the missile coming towards you, and it got big enough to where you could see the fins on it. You could actually see them start to wiggle, and then it dropped out and went away. Everybody was a little excited.
3 years after starting these high-risk experiments, the Airborne Laser Lab still hadn't downed a missile. When the aircraft took off on May 26, 1983, the scientists on board knew that the Air Force was getting impatient. Time was running out.
Sitting on.
Entering the box. 10. Clear to Fox. That's right. Fire. It worked! It worked!
There were quite a few hoorays and hurrahs that day. And that was one of 5 missiles that they shot down. This is an air-to-air missile. And what ALL did is fracture its nose, which made it break lock and made the missile obviously go off target.
That fall, the plane went on to intercept 2 sea-skimming cruise missiles. This archive film reveals how from over a mile away, the laser beam struck a missile's flight control box and triggered a dive into the sea. The military strategists were now convinced that an airborne laser could act as a missile interceptor. Things seemed to be going well. The crew received the traditional hose down to celebrate a successful mission, but they all knew that the experiments had exposed a serious flaw in an airborne laser.
They're clear weather friends. They don't propagate through clouds. They don't propagate through very, very high turbulence conditions, and they don't go through rain. But they do work at night just fine. In fact, they work better in the night.
As it turned out, Even in good weather, maximum range was just a few miles. Beyond that, atmospheric particles disrupted the beam. It was not an effective missile interceptor. So in the mid-80s, the Airborne Laser Lab was shelved. At Kirtland, the dream of airborne laser defense appeared to be over. There would be no peace through light. But in another research lab, an even grander dream was just beginning. Despite progress with arms control treaties, a threat of nuclear annihilation was very real in the early 80s. If an intercontinental ballistic missile was launched from a Soviet silo, it was almost impossible to intercept the transatlantic flight. But some scientists believed there was still a way of using the power of the laser. They drew up plans to put a death ray into space. Although it seemed very ambitious, there was a logic that explained why this laser weapon would succeed when its airborne predecessor had failed. Space-based laser designer Grant Hossack.
Some of the differences between a space-based laser and an airborne laser are the fact that the airborne laser must shoot through at least a little bit of atmosphere, even though it's high up and the atmosphere is thin. Where the space-based laser is way out, where there's essentially zero air. And the space-based laser has the advantage of not having to penetrate through the atmosphere.
This is Alpha, an experiment to test the capabilities of a space-based laser. It's an extraordinary engineering achievement, but few people know of its existence. The precise power of this laser remains secret, but the US military has conceded that it's more than 1,000,000 watts, which would give the laser's range about 5,000 miles in the vacuum of space. This laser's accuracy has never been demonstrated out in space because Alpha cannot leave this huge test chamber in Southern California. It was a ground-based experiment. By the beginning of the 1990s, the military had become disenchanted with the idea of a space-based laser weapon. Even they had begun to wonder if these scientists were chasing a dream rather than engineering a weapon system. So Alpha, the space-based laser, joined its airborne cousin on the shelf. The laser scientists moved on to other projects, but they remained on the lookout for new applications for this technology. In 1990, many of the laser weapon labs at Kirtland lay empty. Peace through light was seen as an intriguing but expensive mistake. Then a new threat emerged when Iraq invaded Kuwait. The Gulf War let military scientists see how various weapon systems performed on the battlefield. The success of high-tech weaponry was relayed to the news networks, but the commanders in the field knew that they had a critical problem. Iraqi Scud missiles, capable of carrying chemical or nuclear warheads, were penetrating the US defenses. Nobody could feel safe in the shadow of this threat. The US Army did have an interceptor missile, the Patriot, and it looked good on TV. But now people claim that the Patriots missed most of the Scuds, perhaps nearly all of them. At Kirtland, when the Patriots' misses became known to the laser scientists, they saw an opportunity to revitalize their quest. And this time, it wouldn't be just an experiment. They would build a weapon that could one day go to war. but they still face the old problem of atmospheric interference that limited the range of the previous airborne laser. At Kirtland Starfire Observatory, astronomers facing a similar problem have developed an optical device that is able to penetrate the atmosphere. At the base of this telescope is an unusual mirror that bends. This attempt to take the twinkle out of the starlight may change the future of laser weapons. The man who pioneered these optics is Air Force scientist Bob Fugate.
The atmosphere has been a problem for astronomers ever since Newton invented the telescope. And actually Newton himself realized that the atmosphere was a limiting factor.
Starfire's main mission is to spy on and track satellites, but it also gazes at the stars.
Okay, let's open the track loop. Track loop's open. We'll get set up here for the next test. Let's try this out here on this fairly bright star.
The star the astronomers are watching tonight is called Mu Cass. Once the telescope is in position, a massive green laser beam is focused to a point 8 miles up in the night sky. The observatory looks at this point first to see how much it's distorted by the atmosphere. The plan is to monitor how the air is behaving.
Let's see, can we acquire the star and close the track loop?
Track loop is closed. Loop's closed at 4-4.
The distortion is viewed as a shifting pattern of dots of light.
That's much worse. Okay, we've got enough signal.
A computer gives the shifts precise values, which are relayed to the mirror that bends. This mirror has tiny motors pushing and pulling its thin glass surface to create minuscule variations.
Getting some improvement here.
The flexible mirror shifts the dots back to where they should be, and the atmospheric distortion is reduced. The telescope can produce an image of Mu Cass that is so sharp the astronomers can see the much smaller star beside it.
Maybe there's something on the left here. And let me stretch the image a bit here.
There it is.
There it is.
Right there. Yep, there it is. Way to go, Bob.
All right.
The laser beacon guiding flexible mirrors improves Starfire's vision by 1,000%. Laser scientists are hoping that Starfire's advances will overcome the atmospheric problem encountered by earlier weaponized lasers.
Got him.
If a working laser defense system can be developed by the U.S. Air Force, it may change war and peace forever.
Launch. Engageable. And firing.
You've been given all the information. Now it's your turn to discuss the questions. Take a moment to talk about the following.
How do lasers work?
How does the military rely on science?
We hope you've enjoyed this assignment discovery analysis of the Lanthanides series. If you'd like to learn more about what you've just seen, go online or check out these books at your local library.